Hi students. In this video, in chapter 10, chemical bonding, we're going to discuss why ionic compounds have their certain mole ratios in their chemical formulas. So the first thing we want to understand is we know that metals form positive charges because they lose electrons, and nonmetals form negative charges, anions, because they gain electrons. And we know that the positive cations and negative anions come together to form an ionic compound. And ionic compounds essentially look like this. They're not really molecules, they're repeating lattice structures. But again, the formula shows our mole ratios. So the positive charge of the metal and the negative charge of the nonmetal is what holds this compound together. We can show this easy and the formula ratio using our concept of Lewis theory and Lewis dot symbols. So the formation of potassium chloride. We've already learned that potassium has a positive 1 charge because it's in group 1A, and chloride has a negative 1 charge because it's a halogen in group 7A, and it wants one more electron, and it gains it to be like a noble gas. And that's why we get the mole ratio 1:1 in potassium chloride. But how can we show this using Lewis symbols? Well, we know that potassium is in group 1A, and it has 1 dot because it has 1 valence electron. So that's period 4, position 1 of the S block. So that's a 4s1. If we look at chlorine, it has 7 dots. Why does it have 7 dots? Group 7A halogen, so it has 7 valence electrons. So what could chlorine do to be happy? It essentially gains this 1 electron and pairs it up from potassium. And potassium's happy to lose this 4s1 because now it can drop down to its 3rd energy level and be stable. And once it does that, once it loses its 1 valence electron, potassium now becomes like argon. And we see this. So how it's denoted is now potassium has a positive charge because it has the electron configuration of argon, which is a 1s2, 2s2, 2p6, 3s2, 3p6. And the chloride ion is happy because it is also like argon with a 1s2, 2s2, 2p6, 3s2, 3p6. Remember, this was a 3s2, 3p5. It had 7 valence electrons in that 3rd energy level and wanted 1 more to be like argon. Potassium was actually a 4s1. It couldn't gain enough electrons to be like krypton. It was easier to lose the 1 and become like argon. So it now has this configuration. But our main concern here is using Lewis symbols to figure out how to get octets, how to lose valence electrons, and come up with our formulas. So if we look at sodium sulfide, sodium is a +1. We know that sulfide is a -2. So when we do our crisscross, we get the mole ratios of Na2S, sodium sulfide. So how does that work? Well, sodium has 1 valence electron that it's going to lose because it's in group 1A. It has this valence electron, which is a 3s1. If you look at sulfide, it's in group 6A, so it has 6 valence electrons. That's why it has 6 dots. Sulfur wants to gain 2 more electrons to be like argon. So how does it do that? It's going to require not 1, but 2 sodiums willing to lose electrons and make that sulfide happy with an octet. So that's essentially what it does. Each sodium loses its 1 valence electron to be like neon in this case, because sodium is 11 valence or 11 electrons, one valence electron, and now it drops down to neon. So it's a 1s2, 2s2, 2p6. When it loses its one valence electron, which is this one, it now drops down to a 1s2, 2s2, 2p6, and it's happy because it has a configuration like the noble gas neon, and it actually now has an octet in its outer shell. The sulfide is happy because it becomes like argon with the two additional electrons, because it was originally a 1s2, 2s2, 2p6, and a 3s2, 3p4. And now with the two additional electrons, it becomes 3s2, 3p6, which is exactly like argon. So I hope that helps you understand how Lewis symbols can be useful in understanding the exchanging of electrons and how we can form the correct formula ratios for ionic compounds.